Good morning, students. In the last session, we discussed about behavior of dielectrics in an external electric field. In this session, we are going to discuss Kirchhoff's laws and Wheatstone's bridge. Kirchhoff's laws. For example, in a simple circuit, it may consisting of capacitors or resistors or batteries. So they are in a series combination or parallel combination. In such type of simple electrical circuits, easily we can find out the current and potential difference by applying the simple formulas of a combination of capacitors, combination of resistors. So in that formula, by using that formulas, easily we can find out the simple electrical circuits. But in case of complicated electrical circuits means the circuit which contains many number of capacitors, many number of resistors, many number of batteries which are in connected in series as well as parallel, combination of all these. So in the type of complicated electrical circuits, we cannot find out the current and potential difference, total capacitance or total resistance by using the simple formulas. So to study that complicated circuits, to analyze that complicated circuits, we use these Kirchhoff's laws. So by using these Kirchhoff's laws, we can find out the current and resistance and capacitance and total potential difference. So all these things easily we can calculate in a complicated circuits by applying these Kirchhoff's laws. So simply by using Kirchhoff's laws, we can find out the current and potential differences in complicated circuits which may contain the number of capacitors or number of resistors or number of batteries which are in series combination or parallel combination. So that type of complicated circuits we use these Kirchhoff's laws. So there are two types of Kirchhoff's laws. The first one is Kirchhoff's current law. So in shortcut this is called KCL, and second one is Kirchhoff's voltage law. So in shortcut we can say KVL. So these are the two Kirchhoff's laws. So first one is KCL, Kirchhoff's current law. So the statement of KCL is the algebraic sum of the currents is equal to 0 at the junction. So junction means it's a common point. It's like a chaurasta. So at chaurasta many number of roads will join there. So this is called a junction. So at this junction many number of wires are connected at the junction. So let us take this is the junction. So at this junction I1, I2, I3, I4, I5, 5 number of currents are gathered at the junction. Now when you observe these five different ways of currents, I1, I2, I3, these are the three currents which are entering into the junction. They are coming into the junction. And I4, I5, these two currents are coming out of the junction. So according to KCL, the algebraic sum of the currents is equals to 0 at the junction. In another word, the sum of the currents which are entering into the junction is equals to the sum of the currents which are leaving from the junction. So according to KCL, here I1, I2, I3, these three currents are entering into the junction. So I1 plus I2 plus I3. That means sum of the currents which are entering into the junction equals to I4, I5. So these two currents are coming out from the junction. They are leaving from the junction. So I4 plus I5. That means this is the sum of the currents which are leaving from the junction. So the sum of the currents which are entering into the junction equals to sum of the currents which are leaving from the junction. That means the algebraic sum of the currents is equals to 0 at the junction. That is called KCL. And similarly, second law is Kirchhoff's voltage law, KVL. According to this law, in any closed circuit, the algebraic sum of the potential difference is equals to 0. In any closed circuit, the algebraic sum of the potential difference is equal to 0. So here it's a simple closed circuit. So here we can find R1, R2, R3, different types of resistors, and a battery of potential difference E. Now according to KVL, here the current is passing from positive terminal of the battery to negative terminal of the battery. So this is the current direction. I is the current which is passing through the circuit. Now Here the battery potential difference is E, and we are moving from positive terminal. So this is our movement direction. So we are moving from positive terminal. So the sign of the potential difference is plus E. When we are starting from the positive. Next, we are moving along the current direction. So this is also current direction. I direction is this one, and we are moving in the same direction as current. In that case, the sign is negative, minus. So here R1 resistor and the current is I. Then according to Ohm's law, the potential difference is IR1, V equals to IR. That is the Ohm's law. So here the potential difference is IR1, and we are moving in same as current direction. So minus IR1. Next, coming to the second resistor. So this is the movement direction, and current direction is also same. So here the potential difference at R2 resistor is IR2. So both are in same direction. Minus IR2. Next, in this way, so same as current direction, the potential at R3 resistance is IR3, so minus IR3 equals to 0. So the algebraic sum of the potential difference in a closed circuit is equal to 0. That is called Kirchhoff's voltage law, KVL. For example, if we move from negative terminal of the battery to positive terminal, in that case, here the signs will become changed. So when you move from negative terminal, then you have take minus, and if you move along in this direction, then in each resistor the sign will become plus. That means our movement direction and current direction both are in same direction. Then we should take the sign as minus, and if our movement direction and current direction both are opposite, in that case the sign will become plus. So in this case we moved along the current direction. So that's why the potential difference at R1, R2, R3 is taken as minus. So this is called KVL, Kirchhoff's voltage law. Next one is Wheatstone's bridge. So this diagram represents Wheatstone's bridge. Here there are four resistors P, Q, R, S. So four resistors are connected according to this diagram. So in this connection we can find four junctions that are A, B, C, D. These are the four junctions. Now in between the junctions A and B we connected a battery of potential E, and in between the junctions C and D we connected a galvanometer G. So this is the construction of the Wheatstone's bridge. Now we can observe the current direction here. So this is the current direction. Now when the current reaches the junction A, it will be split into two ways. I1 amount of current is passing through P resistor, and I2 amount of current is passing through R resistor. And at junction C, again this I1 current will split into two ways. One is I3 current which is passing through the Q resistor, and another amount of current Ig is passing through the galvanometer. So these two currents will add up here, reach the junction D, and from this one it will become I4, and this I4 current and I3 current both will add up at the junction B, and that combined current will pass into the negative terminal of the battery. So in this case, here we can find two junctions C and D. When you apply the KCL, Kirchhoff's current law, at the junction C and D, then what happens? Just observe the junction C. So at junction C, I1 amount of current is entering into the junction, and I3, Ig currents are leaving from the junction. So according to KCL, the sum of the currents entering into the junction equals to sum of the currents leaving the junction. So here what are the entering currents? I1 only. So I1 equals to, and what are the leaving currents? I3 and Ig. So I3 plus Ig. So this is equation number 1. So sum of the currents which are entering into the junction equals to sum of the currents which are leaving the junction at junction C. And similarly, when you apply the KCL at junction D, so at the junction D, I2 and Ig, these two currents are entering into the junction. So sum of the currents entering into the junction, I2 plus Ig equals to sum of the currents leaving from the junction. Only I4 current is leaving from junction D. So I4. So this is equation number 2. So equation 1 and 2 represents KCL when we apply at the junctions C and D. Similarly, when you apply the KVL in a closed circuit A, C, D, A, this is one closed circuit, and another closed circuit is C, B, D, C. So in these two closed circuits, when you apply the KVL, what happened? So just observe the first closed circuit A, C, D, B. I am starting from A. So I am moving in the same as current direction at resistance P. So your current is I1 and resistance is P. Then what is the potential drop here? I1 P. And my finger direction and current direction both are in the same way. That means the sign is minus. So minus I1 P. Next one is from the junction E, this is IG is the current. So the current is going into the galvanometer. So the current is IG and resistance is G. So minus IG G and reach the junction D. And from D to A, so our movement direction is D to A, but current is moving from A to D. So what is the potential difference here? I to R. So our movement direction and current direction both are in opposite. So the sign will become plus. So plus I to R equals to 0. So this is equation number 3. And similarly, when you apply the KVL in the closed circuit C, B, D, C. In this closed circuit, I am starting from the point C. So I am moving in this direction. So my movement direction and current direction both are in the same way. So the sign will become minus. And current is I3, resistance is Q. Then the potential difference is I3Q. So we reach the point B. And from point B to D. So my movement direction and current direction both are in opposite. So the sign will become plus. And current is I4 and resistance is S. So potential difference will become I4S. And from D to C, so my movement direction and current direction both are opposite. So sign will become plus. So current is Ig and the resistance of the galvanometer is G. So the potential difference is Ig equals to 0. Equation number 4. So equation 3 and 4 represents KVL when you apply the enclosed circuits A, C, D, A and C, B, D, C. Now this Wheatstone bridge is said to be balanced when the galvanometer shows no deflection. That means the galvanometer current will become 0. So Ig equals to 0 represents the balancing condition of the Wheatstone bridge. So the bridge is said to be balanced when Ig equals to 0. So substitute this Ig equals to 0 in equations 1, 2, 3 and 4. So when you substitute in equation 1, so Ig equals to 0, this term will become 0. Then what are the remaining terms here? I1 equals to I3. I1 equals to I3. So this is equation number 5. And similarly, in equation 2, when you substitute Ig equals to 0, then this term will become 0. Then the remaining terms are I2 equals to I4. I2 equals to I4. Equation number 6. And similarly, when you substitute Ig equals to 0 in equation 3, so this term will become 0. Then the remaining terms are minus I1p plus I2r equals to 0. So this minus I1p term will go this side, it will become plus. Then I2r equals to I1p. That means I1p equals to I2r. Equation number 7. And similarly, when you substitute Ig equals to 0 in equation 4, so this term will become 0. Then minus I3q plus I4s equals to 0. So when you shift this minus I3q term this side, it will become plus. Then I4s equals to I3q. So I3q equals to I4s. Equation number 8. Then divide equation 7 by equation 8. Then what happens? Equation 7 is I1p equals to I2r, and equation 8 is what? I3q equals to I4s. Now, when you observe the equation 5 and 6, I1 equals to I3. So, I1 equals to I3. So, both will be cancelled. And when you observe the equation 6, I2 equals to I4. So, I2 equals to I4. Both will be cancelled. Then what are the remaining terms? Therefore, P by Q equals to R by S. So, this is the condition for the balancing of Wheatstone's bridge. So, this is our today's topic, Kirchhoff's laws and Wheatstone's bridge. Thank you.